In the summer of 2012, inside a control room in California, a group of scientists were watching a stream of data from a spacecraft they had launched 35 years earlier. It was never supposed to still be transmitting. The mission was meant to last 5 years, but Voyager 1 was still alive, more than 18 billion kilometers from Earth. And on a single day in August, two of its readings moved in opposite directions at the same time. The particles it had been swimming through for its entire journey dropped almost to zero, and something else, radiation from outside the solar system, spiked sharply upward. It had crossed the boundary. No human-made object had ever done that before. What it found on the other side was not what anyone expected. The models said the transition would be gradual, a slow fade from one environment to another. Instead, Voyager hit something closer to a wall. The density of the plasma outside the boundary was roughly 40 times higher than predicted. The magnetic field behaved differently than the physics said it should. And years later, drifting deeper into the space between stars, it picked up something stranger still, a faint, continuous hum, not from a star, not from any known source, just a low, persistent sound coming from interstellar space itself, something no instrument had ever recorded. The edge of our solar system was supposed to be simple, a clean line where the sun's influence ends and empty space begins. It is not simple, it is not empty, and we are only beginning to understand what is actually out there. Today, we go through what Voyager found and what it means for everything we thought we knew about the boundary of our solar system. If space done seriously is what brings you here, subscribe. There is a lot more of this coming. And if this one feels worth it, a like helps more than you'd expect. Let's start at the beginning, with the moment this mission was even possible. In the late 1970s, the outer planets briefly formed a path, not a straight line, but a sequence that could be followed. For a short time, gravity itself offered a route outward. We call this alignment rare, but that word barely holds it. Jupiter, Saturn, Uranus, and Neptune arranged so a spacecraft could move from one to the next, stealing a little speed from each world. This method, a gravitational slingshot, uses a planet's motion to accelerate a passing object without fuel. It turns orbital energy into momentum, and in 1977, it became possible across the entire outer system. Without it, the journey changes completely. Reaching Neptune alone would require about 30 years of direct travel. With it, the same distance could be crossed in roughly 12. The difference is not efficiency, it is feasibility. NASA called it the Grand Tour. The window opened once, then closed for 176 years. The next opportunity would not come until the 22nd century. Two spacecraft were prepared. Voyager 2 launched on August 20th, 1977. Voyager 1 followed 16 days later, placed on a faster trajectory that would carry it past its twin within weeks. Their paths diverged almost immediately, but their purpose remained shared. Each probe weighed about 722 kilograms, close to the mass of a grand piano. Inside were 11 scientific instruments, each designed to study planets, moons, fields, and particles. They were built for a primary mission lasting 5 years. Beyond Jupiter and Saturn, nothing was promised. Their power came from radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. No solar panels could function that far from the sun. The output began near 470 watts and decreases by roughly 4 watts each year. Even at launch, the countdown had already begun. The onboard memory across all computers totaled about 69.63 kilobytes, less than a single modern image. Instructions were written in Fortran, an assembly language, prepared using punch cards, each card a fragment of logic carried by hand. And still, we sent them outward. But the deeper constraint was not engineering, it was timing. Miss the alignment, and the mission collapses. There is no alternate route, no slower version that preserves the same reach. The architecture of the journey itself depended on a celestial coincidence. So the spacecraft left Earth carrying instruments tuned for planets, not for what lay beyond them. They moved toward a region that had no direct measurements, guided by models that would soon be tested. They built it to last 5 years. What it discovered in year 35 was the most important thing of all. A single image frame, processed long after the moment passed, began to shift what we thought was stable. Not a dramatic signal, not an alarm, just a routine calibration step unfolding quietly on a screen. On March 5th, 1979, Voyager 1 reached Jupiter and began returning detailed images of its moons. Expectations were steady and conservative. These distant bodies were assumed to be old, cratered and inactive, shaped only by impacts over time. But one image refused to settle. Linda Morabito, working as a navigation engineer at the Jet Propulsion Laboratory, was refining Voyager's position using a photograph of Io. The task required precision, not discovery. Yet behind the edge of the moon, she noticed a faint, curved shape extending into space. It did not match any known artifact. The structure resembled an umbrella, thin at the base and widening outward, suspended beyond Io's limb. Further analysis confirmed it was real, not a flaw in the image. It was a plume rising from the surface, reaching nearly 280 kilometers above the moon, an active volcano. Until that moment, active volcanism beyond Earth had not been observed. The prevailing view held that small rocky bodies cooled quickly, losing the internal heat required to drive eruptions. Io did not fit that model, but Io was not heated in the usual way. Instead, its energy came from tidal forces, a process where gravity flexes a body repeatedly, generating heat through internal friction. Jupiter's immense pull stretches Io, while the gravitational influence of Europa and Ganymede shifts that pull slightly with each orbit. The result is constant deformation, like kneading a dense material again and again. Inside Io, rock moves under stress. The heat produced by this motion powers widespread volcanism. Voyager observed 9 distinct volcanoes erupting during the flyby itself. One of them changed visibly between the passes of Voyager 1 and Voyager 2, separated by only a few months. The surface told the same story. Impact craters were scarce. Lava flows had resurfaced the moon so frequently that older features were erased almost as soon as they formed. Io became the youngest surface known in the solar system, defined not by age, but by continuous renewal. But the surprises did not end there. Europa, another of Jupiter's moons, revealed a surface unlike any seen before. Smooth plains stretched across it, marked by long fractures and shifting patterns that suggested movement beneath the ice. It looked less like a frozen desert and more like a surface that had once flowed. The implication lingered, and then, almost quietly, another discovery appeared. A faint arc of material surrounding Jupiter, barely visible against the darkness, resolved into a ring system. Thin, dusty, and undetectable from Earth, it had been hiding in plain sight. One encounter, multiple revisions, what we believed about distant moons, about geological activity, about the outer system itself, began to change in a matter of days. The assumptions held for decades no longer matched the evidence now in hand. Io rewrote the rules for what a moon could be. It would not be the last rewrite. Before any image sharpened, Saturn was already familiar to us, a distant disk with pale bands, encircled by rings that seemed smooth and continuous, like a single structure held in place. But on November 12, 1980, that simplicity began to separate. As Voyager 1 approached, the rings lost their uniform appearance. What had looked like broad bands from Earth resolved into thousands of narrow ringlets, each one distinct, each following its own path. Instead of a few clean divisions, there were countless structures, layered and interwoven, extending across hundreds of thousands of kilometers. The system was not simple, it was intricate. Within the B ring, something stranger appeared. Dark radial features, later called spokes, stretched across the rings like shadows cast from within. They rotated with the rings themselves, not according to orbital motion predicted by classical gravity. Their behavior suggested another force at work: electromagnetism. Charged particles, interacting with Saturn's magnetic field, were lifting fine dust slightly above the ring plane, creating transient patterns that formed and vanished over time. Gravity alone could not explain what we were seeing. The rings were responding to fields as well as mass. And then, smaller bodies revealed their influence. Tiny moons, some only a few kilometers across, were found embedded within or near the rings. These became known as shepherd moons, objects whose gravity confines ring particles into narrow lanes. By pulling material inward on one side and outward on the other, they maintained sharp edges and gaps that had long puzzled observers. The structure of the rings was not accidental. It was maintained, but Saturn held something deeper, hidden behind a uniform glow. Titan, its largest moon, presented a surface that could not be seen. A dense atmosphere composed primarily of nitrogen surrounded it completely. The same gas that fills most of Earth's air existed there in even thicker form, layered with organic compounds drifting high above the surface. Voyager could not see through it. Instead, its instruments detected molecules within the haze, hydrocarbons and nitriles, simple carbon-based compounds that can act as building blocks for more complex chemistry. The atmosphere was active, chemically rich, but visually opaque. We were close, but still outside. The mission plan changed for this encounter. Voyager 1 was directed to pass near Titan, prioritizing its atmosphere over any further planetary visits. That choice altered its path permanently, lifting its trajectory out of the flat plane where most planets orbit the Sun. Beyond that moment, no more worlds awaited. Voyager 2 continued along the original path, heading outward toward Uranus and Neptune. But Voyager 1 began a different journey, leaving behind the remaining planets in exchange for a closer look at a single moon. The decision carried weight. After Saturn, there were no more planned encounters. The spacecraft moved away from the Sun's familiar system, its instruments turning toward regions that had never been measured directly. The rings had become complex, the forces had become layered, and Titan remained concealed. Titan was hiding something, but Voyager couldn't see through the haze. That question would wait 25 years. The path outward narrowed until only one spacecraft remained on it. Voyager 2 continued alone, moving toward planets no probe had ever approached, carrying instruments still waiting for questions we had not yet formed. In January 1986, it arrived at Uranus. The planet did not behave as expected. Its axis, the imaginary line it spins around, was tilted by about 98 degrees, so extreme that Uranus rotates almost on its side. Instead of spinning upright, it rolls around the Sun, exposing each pole to decades of light and darkness. Something had happened long ago. The leading explanation is a massive collision, an impact large enough to tip the entire planet over without tearing it apart. The result is a world where seasons last decades and sunlight moves in ways unlike anywhere else in the system. But the strangeness continued below the visible layers. Uranus possesses a magnetic field, a region of space shaped by the planet's internal magnetism that guides charged particles. On Earth, this field is roughly aligned with the rotational axis. On Uranus, it is not. The field is tilted by about 60 degrees and shifted away from the planet's center, creating a magnetosphere, a magnetic environment that is uneven and unstable. Particles move unpredictably there. Voyager discovered 11 new moons during this encounter. Among them was Miranda, a small body with a surface that seemed assembled from mismatched pieces. One feature stood out, a cliff rising nearly 20 kilometers high, the tallest known drop in the solar system. Its origin remains uncertain, suggesting processes that disrupted and rebuilt the moon over time. But the journey did not pause. By August 1989, Voyager 2 reached Neptune, the final major planet along its path. The distance alone marked the end of one phase, but the environment revealed something unexpected. Neptune, despite receiving far less solar energy, drives winds that reach over 2,100 kilometers per hour, the fastest measured anywhere in the solar system. Energy was being generated internally. A vast storm appeared in its atmosphere, later named the Great Dark Spot. It rotated steadily, comparable in size to Earth itself. Yet when later observations were made in 1994, the storm had vanished entirely, leaving no clear trace of where it had gone. And then there was Triton. Neptune's largest moon orbits in the opposite direction of the planet's rotation, a retrograde motion that suggests it was not formed there. It is likely a captured object from the outer solar system, drawn inward and held in place. Its surface temperature rests near negative 235 degrees Celsius, among the coldest measured anywhere. And yet Voyager observed activity. Dark plumes extended upward from the surface, stretching for kilometers. These were geysers, driven not by liquid water, but by nitrogen gas. A small amount of sunlight passes through Triton's translucent ice, warming subsurface layers just enough to build pressure. That pressure eventually escapes, venting material into the thin atmosphere. Activity in extreme cold. The final encounter left no simple pattern. Worlds tilted, fields misaligned, storms appearing and disappearing, surfaces reshaped under minimal energy. Each observation added a new condition, a new exception. Triton's geysers shouldn't exist. They were the last planetary surprise before both Voyagers turned their instruments toward the unknown. Distance begins to change meaning once the last planet falls behind. The familiar markers disappear, and what remains is not empty, but unmeasured, shaped by forces that do not announce themselves. After Neptune, both spacecraft drifted out of the flat plane where most planets orbit. Their paths angled upward and outward, leaving behind the structured geometry of the solar system and entering regions that had never been sampled directly. But even here, the sun still reaches. It continuously releases a stream of charged particles called the solar wind, a flow of electrons and protons moving outward in all directions. Near Earth, this wind travels at several hundred kilometers per second, and in some regions, it can approach 750 kilometers per second. This outflow does not disperse immediately. Instead, it pushes against the surrounding interstellar medium, inflating a vast region where the sun's magnetic field and particle stream dominate. This region is called the heliosphere, a real structure, not an abstraction, extending far beyond the orbit of the outer planets. Inside it, conditions are shaped by the sunday. Outside it, they are not. The heliosphere acts as a boundary layer between our system and the broader galaxy. It reduces the intensity of galactic cosmic rays, which are high-energy particles accelerated by distant supernova explosions. Without this shielding, the radiation reaching Earth would be significantly higher, altering conditions at the surface over long periods. But the boundary itself remained uncertain. The outer edge of the heliosphere is known as the heliopause, the point where the outward pressure of the solar wind balances the inward pressure of interstellar space. For decades, it existed only in models. No instrument had ever crossed it, and no direct measurement confirmed its location. Estimates varied. By the 1990s, predictions placed the heliopause somewhere between 100 and 150 astronomical units from the Sun, where one astronomical unit equals about 150 million kilometers. Even this range was uncertain, shaped by incomplete data and assumptions about the surrounding medium. Voyager was moving toward it slowly. Years passed, then decades. As it traveled, it encountered regions where the solar wind weakened, where particles slowed, where the influence of the sun began to change in ways not fully understood. Each layer revealed new behavior, suggesting that the boundary was not a single surface, but a sequence of transitions. But the heliosphere itself is not stationary. The sun moves through the galaxy at about 26 kilometers per second, heading toward the constellation Hercules. As it travels, it carries the heliosphere with it, compressing the leading edge and stretching the trailing region behind. This motion gives the structure a shape. The front becomes a blunt nose facing the direction of travel. The rear extends into a tail, though its exact form remains uncertain, influenced by magnetic fields and external pressures that are still being mapped. The boundary was ahead, but its position, its shape, and its behavior remained unknown. There were no direct observations, only expectations built from theory and partial evidence. Nobody knew exactly where the edge was. Nobody knew what it looked like. Voyager was about to find out, and it would take longer than anyone expected. Pressure builds quietly in regions we cannot see until motion itself begins to change. Outward flow does not continue forever, and at a certain distance, it meets resistance that cannot be ignored. The solar wind expands until it encounters the opposing pressure of interstellar space. This pressure is not solid, but it acts like one. The particles slow abruptly, not over millions of kilometers, but across a relatively thin region. This boundary is called the termination shock. A shock, in this context, is a sudden change in speed and energy, where a fast flow becomes slower and more compressed. The solar wind, moving faster than the speed of sound in plasma, a gas of charged particles, drops to subsonic speeds here. Models had predicted where this would occur. Before direct measurements, estimates placed the crossing somewhere between 80 and 100 astronomical units from the Sunday. But the first crossing did not follow a simple line. Voyager 1 reached this region in December 2004 at approximately 94 astronomical units. Yet the crossing was not singular. The boundaries shifted, moving back and forth, so the spacecraft passed through it 3 separate times as conditions changed. The edge was unstable. Voyager 2 encountered the same region in August 2007, but at a different distance, about 83.7 astronomical units. This difference revealed something important. The heliosphere was not symmetric. One side extended farther than the other. The cause lay outside. The interstellar magnetic field, a large-scale magnetic influence present in the surrounding medium, presses unevenly against the heliosphere. Where this pressure is stronger, the boundary is pushed inward. Where it is weaker, the boundary extends outward. The bubble is shaped by its environment. But the first real surprise came from what was missing. For decades, scientists had predicted that anomalous cosmic rays would be strongly accelerated at the termination shock. These are particles that originate within the heliosphere, then gain energy at the boundary, becoming a distinct population. Nearly every model supported this outcome. Voyager did not confirm it. Instead, the measured levels were only 5 to 10% of what had been expected. The discrepancy was not small. It was off by factors of 10 to 20, a gap large enough to challenge the underlying assumptions. The result became known as the Voyager paradox. The expected signature of acceleration was largely absent. The mechanism thought to dominate the region did not appear in the data where it was supposed to be strongest. The boundary behaved differently than predicted. But a revised understanding began to emerge. The shape of the termination shock is not a perfect sphere. It is blunt at the front, facing the direction of motion, and extended along the sides. Particle acceleration appears to occur more efficiently along these flanks, far from the path Voyager followed. Location mattered. The spacecraft had crossed near the nose of the heliosphere, where conditions were less favorable for the process scientists expected to observe. The absence was not a failure of physics, but a limitation of perspective. The shock had been crossed, but the structure was more complex than a single surface. Voyager 1 crossed the termination shock in December 2004, and the very first thing it measured there destroyed 20 years of theory. The data did not transition cleanly. It shifted into a pattern that did not belong to any known region, as if the spacecraft had stepped into a space that had no definition yet. On July 28, 2012, Voyager 1 entered a zone that resisted classification. It was no longer behaving like the heliosphere we had modeled, but it did not match expectations for interstellar space either. Two streams began to appear together. Galactic cosmic rays, particles arriving from outside the solar system, increased sharply and began moving inward along the magnetic field. At the same time, solar energetic particles originating from the sun continued flowing outward along those same lines. Both directions existed at once. The magnetic field, an invisible structure that guides charged particles, had become a shared pathway. Instead of separating environments, it was linking them, allowing material from two distinct regions to move simultaneously through the same channels. Scientists gave this region a name. They called it the magnetic highway, a term meant to describe aligned magnetic field lines that allowed particles to travel with minimal obstruction. It was not a boundary, not a gradual transition, but a corridor where movement became unexpectedly efficient. Nothing like it had been predicted. No model had included a region where inward and outward particle flows could coexist in such a stable configuration. The heliosphere was expected to shield, to separate, to maintain a clear distinction between inside and outside. But this region blurred that distinction. The most critical measurement came from the direction of the magnetic field itself. In theory, crossing into interstellar space should involve a noticeable change in orientation, since the sun's magnetic field and the interstellar magnetic field originate from different sources. The direction did not change. Across multiple crossings into and out of this region, the field remained nearly aligned with its previous orientation. This result carried weight. If the direction stayed the same, then Voyager had not yet entered a new magnetic environment. But it was no longer behaving like the old one. This contradiction shaped the debate that followed. Some scientists argued that the spacecraft had already crossed the heliopause, the outer boundary. Others maintained that it remained within a modified region of the heliosphere. Both interpretations had support. Papers were published presenting opposing conclusions, each grounded in valid measurements. The disagreement was not due to error, but to the structure itself. The region did not fit existing categories, so the data could not resolve cleanly into a single interpretation. We were observing something unmodeled. The magnetic highway represented a new layer, a structure that existed between definitions, discovered not through prediction, but through direct encounter. It suggested that the outer boundary of the solar system was more complex than a simple surface. Then, within weeks, the situation changed. The magnetic field direction didn't change, which meant Voyager hadn't actually crossed into interstellar space yet. It was in something else, something with no name. The graphs did not slope or taper, they broke. Lines that had drifted for decades suddenly dropped, as if a switch had been thrown somewhere far beyond reach. On August 25th, 2012, the particle counts changed within a single day. Solar particles, detected continuously for 35 years, fell to near zero. The signal did not fade. It vanished. At the same time, another population surged. Galactic cosmic rays rose sharply and settled into a new baseline, higher and stable, unlike anything recorded before along the spacecraft's path. These are high-energy particles that originate far outside the solar system, moving across interstellar space with enormous energy. The transition was immediate. It did not resemble a gradual thinning or mixing. It resembled a boundary, abrupt and defined, sharper than any model had predicted. One environment ended. Another began. Voyager 1 had reached approximately 121.6 astronomical units from the Sunday. At that distance, the outward pressure of the solar wind no longer dominated. The spacecraft had crossed the heliopause, but the confirmation did not come quickly. The data required careful examination, independent analysis, and time. NASA did not announce the crossing until September 12, 2013, more than a year later. The evidence had to be certain. The key measurement came indirectly. In April 2013, a solar shock wave, a pressure pulse from an earlier solar event, reached Voyager's position. As it passed, it caused the surrounding plasma, a thin gas of charged particles, to oscillate, producing measurable waves. These oscillations revealed the local electron density. Electron density, the number of electrons per unit volume, acts as a signature of the environment. Inside the heliosphere, it remains low. Outside, in interstellar space, it increases. The measured value was about 0.055 electrons per cubic centimeter. This was roughly 40 times higher than the density recorded within the heliosphere. The difference was not subtle. It confirmed that Voyager was now immersed in a fundamentally different medium. We were no longer inside. No spacecraft had ever reached this region before. There were no calibrated expectations, no prior measurements to compare against. Every reading represented a first encounter, a direct sample of a space that had only existed in theory. The boundary had been crossed, but the nature of what lay beyond did not align with assumptions. The transition was sharper, the densities higher, the structure more defined than predicted. Instead of a gradual blending, there was a distinct shift, a wall, not a fade. The data forced a reconsideration of how the heliosphere interacts with its surroundings. It was not a soft edge dissolving into space, but a boundary with structure and behavior of its own. Voyager 1 had crossed into interstellar space, but what it found there was not the quiet void anyone expected. Temperature does not always behave the way we expect it to. It can rise sharply even where matter itself becomes almost absent, creating conditions that seem contradictory when viewed through everyday experience. As Voyager moved across the heliopause, its instruments recorded a sudden increase in plasma temperature. Plasma, a gas made of charged particles, responds to electromagnetic forces and carries energy in ways that differ from ordinary air. The readings were extreme. Estimates placed the temperature between 30,000 and 50,000 degrees Celsius. This range exceeds the visible surface temperature of the Sun, a comparison that immediately challenged existing models of the region. But the expectation had been different. Before direct measurement, the interstellar medium was assumed to be relatively cooler than the solar wind environment, closer to the Sunday. The transition was expected to involve a drop in temperature, not a sharp rise. Instead, the boundary revealed something active. Scientists began referring to this region as a wall of fire, not because it contains flames, but because it marks a zone where energy concentrates as two different plasma environments meet and interact. It is a boundary defined by motion and pressure rather than solid structure. The underlying process involves magnetic reconnection. This occurs when magnetic field lines from different regions come into contact, break, and reconnect in new configurations. During this process, stored magnetic energy is released rapidly, accelerating particles and generating heat within the plasma. The boundary becomes a site of transformation. Voyager 2 provided independent confirmation years later. When it crossed the heliopause in November 2018, its functioning plasma instrument measured a similar temperature increase, identifying a thin, highly energized layer present on both sides of the boundary. The pattern was consistent, but the conditions introduce a subtle distinction. Temperature measures the energy of particles, how fast they move. Heat, in a practical sense, depends on how many particles are present to transfer that energy. In this region, the density is extremely low, close to a vacuum. Very few particles exist. So even though individual particles carry high energy, there are not enough of them to transfer significant heat to a passing object. Voyager moved through this region without damage, not because it was shielded, but because there was almost nothing there to interact with its surface. Energy without contact. This combination alters how we interpret the boundary. It is not simply a dividing line between two spaces. It is a dynamic region where fields reconnect, particles accelerate, and energy redistributes in ways that models had not fully captured. The measurements suggest activity rather than stillness. The heliopause is not passive. It behaves as a system where forces meet, adjust, and evolve over time. Each reading adds detail to a process that cannot be seen directly, only inferred through its effects. The temperature was off the charts, the density was almost nothing, and the magnetic field was pointing the wrong way. Or was it the right way? Nobody could agree. Direction was supposed to be the clearest signal of all. A simple change in orientation, a clean rotation, something unmistakable that would tell us we had moved from one magnetic environment into another. That expectation was built into every model. When a spacecraft crosses the heliopause, the Sun's magnetic field should give way to the interstellar field, and the angle of those lines should shift noticeably. Different sources, different structures, different directions, but the measurement did not follow that script. In 2012, Voyager 1 recorded a magnetic field that remained nearly parallel across the boundary. The direction before and after the crossing aligned closely, as if nothing fundamental had changed. It was not a small deviation. The lack of rotation challenged one of the most basic assumptions about the transition between these regions. If the direction stayed the same, then the boundary itself might not behave as a clean separation. The initial response was cautious. Scientists examined the instruments, the calibration, the possibility of error. When data contradicts expectations so directly, the first step is to question the measurement itself. Could the magnetometer be misreading the field or responding to some local effect? Another explanation was considered. Perhaps the crossing point itself was unusual, a specific location where the alignment happened to match by coincidence. If so, the result might not represent the boundary as a whole, only a narrow region shaped by local conditions. But a single data point is never enough. Years later, a second opportunity arrived. On November 5th, 2018, Voyager 2 crossed the heliopause at a different location, far from the original path, separated by billions of kilometers and positioned along another part of the boundary. Its instruments were still active. The magnetometer on Voyager 2 measured the field direction as it moved across the boundary. The result matched the earlier observation. The magnetic field beyond the heliopause remained nearly parallel to the field inside. Two independent crossings. Two separate spacecraft using different instruments, encountering the boundary at different positions, and both returning the same unexpected alignment. The explanation of coincidence no longer held. The result became structural. The heliopause was not producing the rotation that had been predicted. Instead, the interstellar magnetic field appeared to be interacting with the heliosphere in a way that aligned the outer regions, shaping the boundary before the crossing even occurred. The implication extends outward. If our solar system's boundary behaves this way, then other stars moving through the galaxy may form similar structures where magnetic fields connect and align rather than separate sharply. The interaction between stellar systems and the interstellar medium may be more organized than previously assumed. The boundary becomes a region of influence. Fields do not simply meet and change direction. They adjust, merge, and reshape each other over large distances, creating continuity where discontinuity was expected. Two spacecraft, billions of kilometers apart, in different parts of the boundary, and both found the same impossible thing. Numbers began to separate in ways that could not be smoothed out. Values that had remained stable for years suddenly shifted, not by small margins, but by orders that demanded a different interpretation. At the boundary, Voyager 1 measured electron density, rising from about 0.002 electrons per cubic centimeter to roughly 0.055. Electron density, the count of charged particles within a given volume, serves as a direct indicator of the surrounding medium. The increase was about 40-fold. This was not a gradual transition. It was a step change, consistent with entering a region where the background conditions were fundamentally different. The spacecraft had moved into a denser plasma environment, even though the overall density remained extremely low by terrestrial standards. Voyager 2 confirmed the pattern. When it crossed the heliopause in November 2018, it recorded a similar rise, about 20 times higher than the values inside. The results were detailed across 5 coordinated studies published in Nature Astronomy, each focusing on a different instrument and measurement. The agreement mattered. 2 crossings, 2 locations, 2 sets of instruments, all pointing to the same conclusion. The boundary was associated with a sharp increase in particle density, but the structure itself was more complex than a simple edge. Compression appeared on both sides. Instead of a clean division, the plasma showed signs of being squeezed from both directions. Pressure from the solar wind and pressure from the interstellar medium met and interacted, raising density locally in a narrow region around the boundary. But the boundary did not remain intact. Before Voyager 1 fully crossed, its instruments detected intrusions of interstellar particles extending inward, narrow streams that penetrated the heliosphere ahead of the main transition. These were not isolated events. They formed patterns, suggesting that the boundary allowed selective passage. Voyager 2 observed the reverse. Low-energy particles originating from the Sun were detected far beyond the heliopause, extending outward over distances exceeding 160 million kilometers. Material from inside the heliosphere was leaking outward into interstellar space. Flow in both directions. The heliopause was not a sealed surface. It behaved more like a permeable layer, allowing particles to cross under certain conditions, guided by magnetic fields and local pressure differences. Location influenced the behavior. Voyager 1 crossed near the nose of the heliosphere, the region facing the direction of the Sun's motion through the galaxy. Voyager 2 crossed along the flank, a region offset from that leading edge. The flank appeared more porous, allowing greater exchange between environments. The structure varied with position. This asymmetry carries implications that extend inward. If the boundary allows more cosmic rays to enter in some regions than others, then the shielding provided by the heliosphere is not uniform. The distribution of incoming radiation may depend on direction and change over time. The sky itself becomes uneven. As the Sun moves through the interstellar medium, the shape and permeability of the heliosphere adjust, altering how effectively it filters incoming particles. The protective effect is dynamic, not constant. The heliosphere was not a sealed bubble, it was more like a sieve, and nobody had known. Patterns continue even after the boundary is behind us. Instead of leveling out, the measurements begin to drift upward, slowly at first, then with a consistency that suggests something larger unfolding around the spacecraft. Voyager 1 carried a plasma wave instrument, a detector designed to measure oscillations in plasma, the thin gas of charged particles filling space. Even after crossing the heliopause, it continued to track electron density as the spacecraft moved farther outward. The values did not remain fixed. Instead, the density increased gradually with distance, forming a broad gradient that extended away from the boundary. Each new measurement suggested that the surrounding medium was not uniform, but structured in ways that had not been directly observed before. The change was subtle, but persistent. Then, in October 2020, a distinct event interrupted that gradual rise. A pressure pulse from the Sun, originating from earlier solar activity, traveled outward for years before reaching Voyager's position, now near 149 astronomical units. When it arrived, the effect was immediate. The passing shockwave compressed the local plasma, triggering oscillations that allowed the instrument to measure a sharp increase in electron density. The spike was not temporary noise. It revealed conditions that had been building along the spacecraft's path. After the event, the density settled into a higher level. Subsequent readings stabilized near 0.147 electrons per cubic centimeter. This value remained consistent across later measurements, suggesting that Voyager had entered a region with a different baseline density than before. By 2023, the data hinted at something broader. The increase appeared to level into a plateau, possibly indicating that the spacecraft had reached a region of relatively uniform density or a peak within a larger structure. but the interpretation remained uncertain. What is shaping this pattern? One explanation lies in the nature of the very local interstellar medium, the region of space immediately surrounding our solar system. It is not smooth. It contains variations in density, small-scale turbulence, and gradients that shift over distance. We are moving through structure. Another factor involves motion itself. The heliosphere travels through the galaxy at about 26 kilometers per second, interacting with the surrounding medium. As it moves, it can compress material ahead of it, forming a region of increased density. This is sometimes described as a bow wave, not a sharp front like a shock, but a gradual buildup of denser plasma as the heliosphere pushes forward. The exact shape and extent of this compression depend on the geometry of the heliosphere, which is still under study. The structure is not fully resolved. Each measurement Voyager sends back adds a point to a map that did not exist before. There is no other instrument in this region, no parallel observation to compare against. The data stands alone, and it continues to evolve. The density keeps climbing. The models do not fully explain it. Voyager is mapping a region so new that science is being written in real time, section by section. The signal did not arrive as an event, but as a persistence. It remained in the background, steady and unremarkable, until someone looked closely enough to notice that it never went away. In 2021, researchers at Cornell University revisited years of archived data from Voyager 1. The instrument in question was the Plasma Wave Science System, designed to detect oscillations in plasma caused by passing disturbances. Originally, it listened for shocks. These shocks came from solar events, pressure waves traveling outward for years before reaching the spacecraft. When they arrived, they disturbed the surrounding plasma, creating measurable oscillations that revealed local conditions. But something else was present. Buried in the data, beginning around 2017, was a faint, narrowband signal. Narrowband means it occupies a very specific range of frequencies, not spread out like noise. It was continuous, low level, and did not correspond to any solar event. It was always there. The signal did not spike or fade with activity from the Sunday. It remained steady, a background tone that persisted between the more dramatic events that had originally defined the measurements. The interpretation required a shift. Instead of treating the signal as interference, researchers recognized it as a feature of the interstellar medium itself. The medium, composed of sparse plasma, contains electrons that move due to their thermal energy, the natural motion caused by temperature. This motion produces a faint electromagnetic emission. The signal represents that emission, a constant whisper generated by the random motion of electrons in a very thin plasma. It does not require an external trigger. It is present as long as the medium exists. This changed the method of measurement. Previously, density readings depended on waiting for solar shocks to arrive, events separated by months or years. Now, the continuous signal allowed scientists to estimate electron density at all times, not just during disturbances. A continuous record became possible. Over distances spanning about 10 astronomical units, the data revealed variations in density that had not been resolved before. These fluctuations occurred on large scales, indicating that the interstellar medium is not uniform but contains structure and turbulence. Patterns emerged within the signal. The variations suggested regions of slightly higher and lower density, shaped by processes operating over vast distances. The space between stars was not smooth. It contained movement, variation, and subtle shifts in composition. The analogy offered by James Cordes captures the contrast. A solar shock is like a lightning strike, brief and intense, illuminating the environment for a moment. The continuous signal is more like steady rain, quiet but persistent, revealing the underlying conditions over time. The instrument had been hearing it all along. It required distance from the sun's influence and a different way of listening to recognize that the signal was not noise, but information. The background itself had become measurable. The hum is still there. It has been continuous since 2017. Voyager is listening to the background noise of the galaxy and passing on what it hears. Time stretches differently when distance becomes this large. Events that begin near the sun take years to arrive, carrying their imprint across space until they finally reach a place where no direct measurement was ever expected. The sun occasionally releases coronal mass ejections, vast eruptions of plasma and magnetic field launched outward at high speed. These events generate pressure waves that move through the heliosphere at several hundred kilometers per second, pushing through the surrounding medium. The waves do not dissipate quickly. They travel outward for years, crossing tens of billions of kilometers, maintaining enough structure to interact with the plasma far beyond the planets. When one of these waves reaches Voyager, it disturbs the surrounding particles in a measurable way. The interaction is sudden. As the wave passes, it compresses the local plasma and triggers oscillations, small rhythmic variations in the density of charged particles. These oscillations can be detected and analyzed, providing a direct measurement of the environment at that precise location. A specific event illustrates this clearly. A large solar eruption in 2012 generated a pressure wave that began its journey outward. It moved steadily, crossing the outer regions of the heliosphere, and eventually reached Voyager 1 in April 2013. The distance traveled exceeded 23 billion kilometers. Its arrival was not unexpected. Scientists had predicted when the wave would reach the spacecraft based on its speed and the known distance. When it arrived, the timing matched the prediction closely. This was a new kind of measurement. For the first time, an event originating at the sun was tracked across interstellar distances and used to probe the medium at the edge of the solar system. The wave acted as a tool, briefly illuminating the conditions around Voyager. From this interaction, electron density could be calculated. By analyzing the frequency of the plasma oscillations, researchers determined how many electrons were present in a given volume. Each event provided a single, precise data point tied to both time and distance. The result is a developing map, not a continuous image, but a series of points, each one marking a measurement taken at a specific location. These points extend from about 122 astronomical units outward, tracing the properties of the very local interstellar medium. But the process is slow. Each new data point depends on the arrival of another solar event, and these events are separated by months or years. Between them, the spacecraft continues to drift, waiting for the next disturbance to pass through. The gaps are part of the pattern. Over time, the collected measurements reveal variations in density, regions where the plasma is slightly more concentrated or more diffuse. These variations indicate structure within the interstellar medium, features too large and distant to observe directly from Earth. The region is not uniform. Voyager is not only passing through it, but measuring it in sequence, building a record that did not exist before. Each interaction adds detail, refining our understanding of a space that was once entirely theoretical. Every shock is a data point, Every data point is a depth reading in an ocean nobody has ever mapped. The map is still being drawn. Some measurements depend on survival, not design. Instruments built decades earlier either remain functional or fall silent, and that difference shapes what we are able to know when the moment finally arrives. Voyager 1 lost its plasma instrument in 1980. That system, responsible for directly measuring the temperature and density of charged particles, failed long before the spacecraft reached the outer boundary. When it crossed into interstellar space, it did so without the ability to take one of the most critical readings. It arrived partially blind, but Voyager 2 carried the same type of instrument, and it continued operating. On November 5, 2018, when Voyager 2 crossed the heliopause, it was able to measure the plasma directly, providing the only in situ reading of that boundary ever obtained. The results were not what models had suggested. Inside the heliosphere, the plasma temperature measured near 37,000 degrees Celsius. Just beyond the boundary, the temperature ranged between roughly 30,000 and 50,000 degrees. Instead of cooling, the plasma remained hot, consistent with earlier indirect observations. But the instrument revealed more than temperature. It detected a narrow region at the boundary where plasma density increased and properties began to blend. This transition layer was thin yet distinct, a zone where solar plasma and interstellar plasma interacted directly, neither fully one nor the other. A region of mixing. This layer had not been visible to Voyager 1. Without a functioning plasma instrument, it could not detect the subtle changes in particle behavior that defined this zone. The discovery depended entirely on Voyager 2's continued operation. A single instrument made the difference. The measurement confirmed that the heliopause is not a sharp line. It is a structured region with gradients, mixing, and interactions that extend across a finite distance rather than collapsing into a single surface. The crossing became a coordinated observation. On November 4, 2019, NASA released 5 scientific papers simultaneously, each based on data from a different instrument aboard Voyager 2. Together, they formed a composite view of the boundary. Each instrument contributed a piece. The magnetometer showed the field alignment. Particle detectors revealed sharp changes in energetic populations. Low-energy particle sensors traced the outward leakage of solar material. The plasma instrument mapped the temperature and density within the transition layer. The plasma wave system confirmed the surrounding electron density through oscillations. 5 perspectives, 1 event. Taken together, they described a boundary that behaves more like a region than a surface. It is turbulent, allowing particles to pass through under certain conditions. It is shaped by electromagnetic forces, not just pressure. It contains structure that changes over distance. The simplicity had dissolved. What had once been imagined as a clear dividing line became something layered and dynamic, with properties that vary depending on position, energy, and local conditions. The boundary itself became an environment. Each instrument saw a different aspect. No single measurement could capture the full complexity. Only by combining them did the structure begin to emerge, revealing a system more intricate than any one dataset could suggest. 5 separate papers, 5 instruments, all published the same day. What they described together was something richer and stranger than any single instrument could have captured alone. From far away, we once imagined a simple outline, a smooth sphere centered on the sun, expanding evenly in all directions, a protective envelope with no preferred side and no distortion. But the data does not support that shape. As measurements accumulated, the heliosphere began to appear uneven. The region facing the sun's motion through the galaxy is compressed, while the opposite side stretches outward. The structure is not balanced. It is shaped by motion and external pressure. The front is shorter. The rear extends farther. This asymmetry reflects the environment beyond the solar system. The interstellar medium exerts pressure that is not uniform, and the magnetic field embedded within it interacts with the heliosphere in ways that distort its form. Recent models go further. Combining Voyager data with observations from the Interstellar Boundary Explorer, a spacecraft that maps energetic neutral atoms, researchers suggest that the heliotail may not extend as a single long stream. Instead, it may divide into two lobes, curved and bent by the surrounding magnetic field. The shape becomes more complex. Rather than a comet-like tail, the structure may resemble a crescent or a deflated balloon, with regions folding and separating under external influence. The exact geometry remains under study, but the symmetry once assumed is no longer supported. This geometry has consequences. The heliosphere acts as a shield against galactic cosmic rays, high-energy particles arriving from outside the solar system. Its shape determines how effectively that shielding works in different directions. Protection is not uniform. Some regions of space above Earth's orbit may be more exposed than others, depending on how the heliosphere is compressed or extended along those lines. The incoming radiation can vary with direction, not just intensity. The surrounding field is stronger than expected. Measurements indicate that the interstellar magnetic field is 2 to 3 times stronger than earlier models predicted. This increases the pressure exerted on the heliosphere, compressing it more than anticipated. A tighter structure results. A stronger external field reduces the overall size of the heliosphere and may make it more sensitive to changes in the surrounding medium. Variations in density or magnetic strength could alter its shape over time. The sun does not remain in a single environment. As it orbits the galaxy, it passes through regions of differing density and magnetic structure. Some of these regions are denser, containing more material that can compress the heliosphere further. The boundary responds. If the heliosphere becomes more compressed, the level of cosmic ray shielding decreases. Higher energy particles can penetrate deeper into the solar system, reaching Earth in greater numbers. This has long-term effects. Increased cosmic ray flux can influence atmospheric chemistry and may contribute to changes in climate over geological timescales. It can also affect mutation rates, subtly shaping the course of biological evolution. Evidence exists. The geological record contains periods where cosmic ray exposure appears elevated, aligning with models of the sun's movement through denser interstellar regions. These patterns suggest that the heliosphere's shape and strength have changed before, and they will change again. The shape of our bubble determines how much radiation reaches Earth, and the shape may be changing, driven by a galaxy that does not hold still. There is a delay built into every decision now, not a pause, but a fixed span of time that cannot be shortened, a distance translated directly into waiting. A signal from Voyager 1 takes about 22 hours and 31 minutes to reach Earth, traveling at the speed of light. That is one direction only. When we send a command back, it requires the same time again, creating a loop that stretches across nearly 2 full days. Every action unfolds slowly. A command is written, transmitted, and then silence follows. Nearly 44 hours pass before confirmation returns. By then, the situation that prompted the command may already have changed. But the spacecraft itself is limited. Voyager's onboard computers contain a combined memory of about 69.63 kilobytes. This is less than a single small image file by modern standards, and tens of thousands of times less than what everyday devices now carry. The software reflects its era. It was written in Fortran and assembly language, constructed using tools and methods that are no longer common. Engineers today rely on printed manuals and, at times, the memory of retired colleagues who helped design the system decades ago. The hardware continues to age. At launch, the spacecraft generated roughly 470 watts of power. Over time, that output has declined to under 250 watts as the radioactive source slowly decays. Each instrument draws from that limited supply. Choices must be made. Systems are turned off one by one, permanently, to preserve energy for the remaining instruments. By April 2026, only 2 scientific instruments remain active. Each shutdown is irreversible. But maintaining orientation is just as critical. The antenna must remain pointed toward Earth, or communication is lost. This requires small thrusters to adjust the spacecraft's position, correcting for drift over time. Some of those thrusters had not been used for decades. In September 2024, engineers performed a thruster swap, switching to a backup set that had been idle since 2018. The goal was to use a less degraded system to maintain control. Then, in May 2025, another step was taken. Thrusters that had been dormant since 1980 were brought back online. These trajectory correction thrusters had remained unused for 45 years, yet they were needed to compensate for the gradual decline of the primary system. Everything now depends on what still works. The spacecraft has entered a single string state, meaning there are no backups for most systems. If a critical component fails, there is no redundancy to take over. The mission would end immediately. The team operates at a distance that cannot be bridged. They cannot see the spacecraft directly. They cannot repair it physically. They send instructions into space and wait, relying entirely on signals that arrive nearly 2 days later. Each decision carries weight. Every action, every command, every fix takes 44 hours to confirm. And in November 2023, it stopped making sense entirely. The signal did not stop. It changed. What arrived was still structured in time, still repeating, but it no longer carried meaning that could be read. In November 2023, Voyager 1 began transmitting data that appeared as noise. Not silence, not a loss of carrier, but a stream of garbled output, repetitive and unusable, as if the message had been scrambled before it left the spacecraft. The source was internal. The fault was traced to the flight data system, the onboard computer responsible for collecting, formatting, and encoding all scientific and engineering data before transmission. It is the system that prepares information so it can be understood on Earth. But that system had failed. The difficulty was immediate. The component responsible for reporting the spacecraft's condition was the same component that was no longer functioning correctly. There was no reliable telemetry, no direct description of the problem, only distortion. Engineers were forced to analyze the corrupted signal itself, searching for patterns within the noise that might reveal what had gone wrong. The process required inference, not confirmation, built on fragments of recognizable structure. Time passed without resolution. For 5 months, no usable scientific data was received from the most distant object humanity has ever created. The spacecraft continued transmitting, but the content could not be interpreted. The fault narrowed. Investigation indicated that a single memory chip within the flight data system had failed. This chip stored a portion of the software instructions, and its failure corrupted about 3% of the code. That small portion mattered. The affected section contained critical routines responsible for organizing data into a coherent format. Without it, the system could still send signals, but the structure of the information was lost. There was no backup. The secondary flight data system had ceased functioning in 1981. No redundancy remained. Repair would require altering the existing software in place. But memory was limited. The solution involved rewriting the damaged code, then dividing it into smaller segments that could fit into remaining functional memory locations. These fragments would then be linked together, recreating the necessary structure through distributed instructions. Each step carried delay. A patch was prepared, tested, and transmitted. The signal traveled for 22 hours. The spacecraft executed the command. The response required another 22 hours to return. Then the result was known. This cycle repeated, each attempt separated by nearly 2 days. Each adjustment based on limited feedback. Progress was incremental, built from successive refinements. Then, in April 2024, the pattern changed. The returning signal regained structure. Engineering data became readable again, indicating that the system had been partially restored. The spacecraft was once again able to report its condition in a usable form. The repair had worked. A machine more than 25 billion kilometers away, operating on hardware designed in the 1970s, had been reprogrammed through fragments of code sent across interstellar space. In April 2024, the first clean data came back, science resumed, and Voyager kept going. For most of our history, we studied our surroundings from within. Telescopes gathered light that had traveled across space, filtered through layers of plasma and magnetic fields before reaching us, leaving gaps that could only be filled with inference. Direct measurement did not exist. Voyager changed that condition by moving beyond the region where the sun's influence dominates. Its instruments began recording properties of the surrounding medium from within, rather than observing from a distance. We gained a new perspective. The spacecraft now samples the very local interstellar medium, the region of space immediately surrounding our solar system. Here, electron density, magnetic field strength, and particle flux can be measured directly without the distortions introduced by distance and intervening structures. The environment has structure. The sun resides within the local interstellar cloud, a region of warm, partially ionized gas extending for about 30 light-years. This cloud is not isolated. It exists inside a much larger formation, known as the local bubble. The scale increases. The local bubble spans roughly 300 light-years, a cavity of low-density gas shaped by multiple supernova explosions that occurred millions of years before the sun formed. These events expelled material outward, clearing regions and redistributing matter across vast distances. Voyager moves through that history. The plasma surrounding the spacecraft consists largely of particles that originated in those explosions, fragments of stars that ended long before our solar system came into existence. The medium is not static. It carries the imprint of those events. Motion adds complexity. The sun travels through this environment at about 26 kilometers per second. At the same time, the local interstellar cloud moves relative to the sun at a different velocity. The heliosphere forms where these motions interact, shaped by their combined direction and speed. The geometry depends on that interaction. The angle between the sun's motion and the surrounding flow influences how the heliosphere compresses and stretches. Variations in the medium alter its shape, affecting how it filters incoming particles. Voyager provides constraints. By measuring conditions directly, it allows models of stellar environments to be tested against actual data. Before these measurements, predictions about how stars interact with their surroundings relied on indirect evidence. Now we have a reference. Other stars likely generate similar structures, forming their own versions of a heliosphere around their planetary systems. The effectiveness of these structures depends on the surrounding medium, just as ours does. The implications extend outward. Understanding this interaction helps define how radiation environments vary across the galaxy and how conditions near different stars might influence the stability of their planets. But we have only one example. Voyager remains the only instrument that has crossed into this region and reported back. Every measurement it sends defines a part of a system that has never been observed directly before. We live inside a bubble, inside a cloud, inside a cavity, inside a spiral arm. Voyager is the first instrument to measure any of it from the inside. The request did not come from necessity, but from intention. A question was asked not about data, but about perspective, about whether the spacecraft could look back once before continuing outward. By February 14th, 1990, Voyager 1 was already far beyond the orbit of Neptune, more than 6 billion kilometers from Earth. It was no longer visiting planets. It was leaving them behind. But Carl Sagan had been asking for years. He proposed turning the cameras around, pointing them back toward the solar system, toward the place the spacecraft had come from. The idea was simple, but the execution was not. The cameras had been powered down after the Saturn encounter in 1980 to conserve energy. They had not been used for a decade. Reactivating them required careful testing. Engineers needed to determine whether systems designed in the 1970s would still respond after years of inactivity in deep space. The risk was not negligible. A malfunction could interfere with other systems still in use. But the attempt was approved. The cameras powered on. Voyager began capturing a sequence of images, building a mosaic that would eventually include about 60 frames. Together, they formed a portrait of the solar system seen from the outside, not as a place of detail, but as a collection of distant points. The planets appeared small. Jupiter was a pale blur. Saturn slightly more defined. Uranus and Neptune were faint, nearly indistinguishable from background noise. Venus showed as a thin crescent. Mars was barely visible. Earth was different. It did not resolve into a disk. It did not show continents or clouds. It appeared as a single point of light, about 0.12 pixels across, suspended within a narrow beam of scattered sunlight created by the camera optics. Less than 1 pixel. That point contained everything. Sagan later described the image in words that would become widely known, reflecting on what that single point represented. He wrote of everyone you know, everyone you love, every human story contained within that fraction of a pixel. The image carried no measurements. It was not taken to analyze composition or motion. It was taken to provide context, to place the solar system within a larger frame and show how small it appears from a distance. A deliberate act. Few scientific missions are directed toward perspective alone. This was one of them, a moment where the purpose shifted from observation to reflection, using the same instrument to produce a different kind of understanding. The sequence was brief. Once the mosaic was complete, the cameras were powered down again. Energy could not be spent on imaging when the mission had moved beyond that phase. The spacecraft would not take another photograph. It did not need to. The cameras were turned off after the mosaic, permanently. Voyager would never photograph anything again. It only needed to take that one picture. Before the spacecraft left the inner system, something else was placed aboard. Not an instrument, not a sensor, but a message, assembled with the understanding that it might never be received. Both Voyager spacecraft carry a gold-plated copper disk, about 12 inches in diameter, prepared in a span of 6 weeks under the direction of Carl Sagan. It was designed to endure the vacuum of space for immense periods of time. The contents were selected deliberately. 115 images were encoded as audio signals, a method that allows visual information to be reconstructed from sound. Alongside them are greetings spoken in 55 languages, brief messages representing a range of cultures and voices. There are sounds as well: wind moving across land, rain falling, waves breaking against a shoreline, the vocalizations of whales, a mother speaking to her newborn child, the sound of two people kissing. Each recording chosen to represent ordinary moments. Music fills a large portion. About 90 minutes of compositions from different traditions are included, spanning centuries and regions. Johann Sebastian Bach, Ludwig van Beethoven, and a range of folk and ceremonial pieces from around the world are present, along with a recording of Johnny B. Good. The selection was debated. When folklorist Alan Lomax questioned the inclusion of rock and roll, suggesting it was too narrow in scope, Sagan replied that it reflected a real part of human culture. The record was not intended to present perfection, but to reflect variety. One contribution is more personal. Anne Druyen, who helped assemble the record, included a recording of her own brain activity measured as an electroencephalogram. This captures electrical patterns from a specific moment, containing her thoughts about human history, connection, and existence. The record also provides direction. A pulsar map is etched onto its surface, showing the position of the Sun relative to 14 known pulsars. Pulsars are rotating neutron stars that emit regular pulses of radiation, and their timing can serve as a reference system. The map functions as a galactic address. Instructions are included. A stylus is attached, and diagrams explain how to play the record and reconstruct the encoded images. The information is presented in a form intended to be understood without shared language. The material was chosen for longevity. The disk is expected to remain intact for up to 1 billion years in space. It is likely to outlast any structure currently on Earth, continuing its path long after the conditions that produced it have changed. Its trajectory is defined. In about 40,000 years, Voyager 1 will pass within roughly 1.6 light-years of the star Gliese 445. This will be its closest approach to another system for millions of years. It carries a record of a moment. Sounds, images, and patterns selected by a small group, representing a much larger population. The choices reflect what was considered worth preserving at the time. The record will almost certainly never be found. The people who made it knew that. They made it anyway. No instrument has ever turned around to look behind us. Every measurement you have followed so far comes from a single direction, the one facing into the oncoming flow of interstellar space. Both spacecraft crossed on that forward side. They passed through the region where the sun's motion meets the surrounding medium, often called the upwind direction, where pressure is highest and structure is compressed. That tells us how the boundary behaves under direct impact. But the opposite side remains unvisited. The heliotail, the downwind extension of this structure, lies stretched out behind the sun as it moves through the galaxy at about 26 kilometers per second. Its shape is still uncertain. We have only indirect clues. The Interstellar Boundary Explorer, a mission that detects energetic neutral atoms, has tried to map this region from within. These atoms are created when charged particles exchange electrons, becoming neutral and traveling in straight lines. By tracing them back, we attempt to infer structure. But the perspective is limited. You are inside the system, trying to reconstruct its exterior from signals that have already been altered by the journey inward. It is like mapping a coastline while standing in the surf. Some patterns have emerged. Data suggests the heliosphere may not trail a long, comet-like tail at all. Instead, it may form two broad lobes, shaped and bent by the surrounding interstellar magnetic field, a structure more compact than expected. But the interpretation is debated. Different models fit the same measurements, and each assumes conditions we cannot yet verify. Without direct sampling, the uncertainty remains embedded in every conclusion. The scale complicates everything. If the classic tail exists, it could extend for 1,000 astronomical units or more, far beyond the reach of any spacecraft currently operating. Voyager 1, even now, is only around 173 astronomical units from the Sunday. Beyond that lies another boundary. The inner edge of the Oort cloud, a distant reservoir of icy bodies, is thought to begin around 2,000 astronomical units. Voyager will take roughly 300 years to approach that region and tens of thousands more to pass through it. But no mission is heading outward with that goal. For more than 2 decades, a concept called the interstellar probe has been studied, a spacecraft designed to reach distances approaching 1,000 astronomical units within a human lifetime, carrying instruments capable of directly sampling the tail. It remains unapproved. No launch date, no hardware, no trajectory. So we work with what we have. 2 spacecraft traveling along similar directions, offering 2 crossings separated by billions of kilometers, but still confined to one side of a much larger structure. Everything else is inference. Mathematical models, indirect imaging, and assumptions layered over limited data points. Each revision brings us closer, but also reveals how much remains unresolved. But the central question holds. What does the heliosphere look like from behind, where pressure relaxes and structure stretches into the unknown? There is no measurement to answer it yet. We have 2 data points on the boundary of our solar system. Everything else is a model. Voyager gave us the only measurements that exist, and there may never be more in our lifetime. There is no moment when the mission ends. There is only a gradual dimming, measured in watts, counted year by year as the spacecraft continues outward. You can think of it as a slow budget. At launch, the power system produced about 470 watts, generated by radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. That decay is steady and irreversible. Every year, the output falls by roughly 4 watts. Now it sits near 230. Each instrument draws from that shrinking supply. The magnetometer measures magnetic fields, the plasma wave system listens to charged particle oscillations, and the cosmic ray instrument counts high-energy particles arriving from outside the solar system. They cannot all survive. Engineers choose carefully. One system is powered down, then another, each decision permanent, each trade shifting the balance between knowledge and time. The goal is simple: extend the mission as long as possible. But extension has limits. By the late 2020s, projections suggest the remaining science instruments will no longer receive enough power to function. When that moment arrives, the spacecraft will still be alive, but its ability to observe will be gone. Only telemetry remains. Telemetry is the stream of engineering data: temperatures, voltages, system states, the internal condition of the spacecraft itself. It is not discovery, but it is still presence. It tells you the machine endures. but even that will fade. The transmitters require power. The antenna must remain precisely pointed toward Earth, maintained by thrusters that themselves depend on the same diminishing supply. Each subsystem draws from the same source. Eventually, there is not enough. No propulsion remains to alter the path. Voyager now travels at about 61,000 kilometers per hour, a constant motion set decades ago, carrying it deeper into interstellar space without correction or return. It becomes a drifting object, a constructed thing, moving through a medium no human will ever physically enter, its trajectory shaped only by gravity and the initial conditions of its launch. It will continue like this for millions of years, but it will not speak. The final transmission will not announce itself. There will be no message that says, "This is the end." Instead, you will receive a carrier signal, a steady radio tone carrying encoded data, the electronic equivalent of a pulse. Then the signal will weaken. Then it will stop. On Earth, receivers will continue listening, waiting for a return that does not come, measuring noise, searching for structure, confirming absence through repeated silence. The distance, more than 22 hours at the speed of light, will remain unchanged. The spacecraft will not know. It will continue outward, systems inert, instruments dark, carrying the gold-plated record fixed to its side. A physical archive designed to endure for up to 1 billion years in the vacuum between stars. But it will not be heard again. One day, there will be a last signal. It will come back across 22 hours of empty space, and then nothing. The room where the signal arrives is quiet, not because nothing is happening, but because everything depends on something you cannot hear. A faint carrier tone. It has traveled for more than 22 hours at the speed of light, crossing distances that no person in that room will ever physically traverse, arriving as a whisper embedded in noise. You are listening with machines. The Deep Space Network uses antennas 70 meters wide, cooled to reduce thermal noise, pointed with extreme precision toward a location that shifts slowly against the stars. The signal you receive is about 20 billion times weaker than the power needed to run a digital watch. But it is enough. Enough to decode, enough to interpret, enough to continue a conversation that has lasted nearly half a century. That conversation is carried by people whose lives have unfolded alongside the spacecraft itself. Ed Stone began as chief scientist in 1972. He remained in that role for 50 years, long enough to watch the mission pass every original milestone, then continue far beyond them, into regions no one expected to reach. He saw data from a machine he helped design as a young man arrive from beyond the heliopause. Others built it beside him. In the 1970s, the engineers working on Voyager were in their 20s and 30s, writing software in Fortran and assembly, encoding instructions on punch cards, solving problems that had no precedent. Today, many of them are in their 70s or 80s. Some are gone, but their knowledge remains active. When anomalies appear, the current team turns to printed manuals produced decades ago, documents that describe systems in a language no longer widely used. They call retired engineers, sometimes late at night, asking how a circuit was designed, why a decision was made. You are hearing voices across time. Suzanne Dodd, who now manages the mission, describes the spacecraft as single string, meaning there are no backups left. Every component, still functioning, is the only one of its kind on board. If it fails, it is final. The team knows this with every command they send. Each instruction travels outward for 22 hours, executed by a machine they cannot see, then returns as a response another 22 hours later. You wait nearly 2 days. and you do it again. But the connection itself demands resources. The large antennas must be dedicated to Voyager during communication windows because the signal is so faint that sharing time risks losing it entirely. You commit entire facilities to a whisper. The people listening now are part of a chain that began before many of them were born. Some of the scientists receiving data today entered the field long after launch, inheriting a mission already older than their careers. They will be the last. When the signal ends, there will be no recovery, no future generation able to re-establish contact. The distance will be too great, the power too low, the geometry too fixed. This has not happened before. A machine, built by human hands, operating perfectly, continuing its path, but slipping beyond the reach of communication purely because of time and space. Some of the scientists receiving Voyager's data today were not born when it launched. The mission spans generations in the most literal sense. If you look outward today, there is no second wave behind it, no distant signal closing the gap, no newer instrument tracing the same path with clearer eyes. There is only one trajectory. The next farthest spacecraft is New Horizons, moving outward at a great distance from the Sun, but still only around 58 astronomical units away as of 2025. It is less than halfway to the heliopause and not aligned to cross it directly. Its path is different. It was designed for a flyby of Pluto and the Kuiper Belt, not for the boundary we have been following. Its instruments are not configured to study the interstellar transition in the same way, and its course will not carry it through the same regions. So the gap remains. There is no mission currently funded to reach interstellar space again. Concepts exist, studied in detail, refined across decades, but none have left the ground. The most developed of these, often called the interstellar probe, would carry modern instruments outward to distances approaching 1,000 astronomical units. It would arrive in about 50 years. With that journey, you could measure the heliotail directly, resolve the asymmetry of the heliosphere, map the outer structure of the Sun's influence, and approach the inner boundary of the Oort cloud, a region we have only inferred from theory and distant observations. But it has not been approved. The challenge is not technical alone, it is temporal. The return on such a mission extends beyond typical political cycles, beyond funding horizons that prefer results within a few years. A 50-year timeline asks for continuity that institutions rarely sustain, so nothing follows. Meanwhile, the existing spacecraft continue their work, their instruments dimming one by one as power declines, each shutdown removing a capability that cannot be replaced. The data they send now is not supplementary, it is singular. Every measurement arriving from that distance is something no other instrument can provide, a direct sample of a region otherwise accessible only through models and indirect inference. When a reading comes in, it is not compared against a second source. It becomes the only source. But this situation is unusual. In most periods of exploration, the first voyage is followed quickly by others, expanding knowledge, confirming observations, correcting errors. Maritime routes, polar expeditions, even early space missions followed this pattern. Here, the pattern breaks. Decades have passed without a successor crossing the same boundary. The instruments still operating were built when software was stored on punch cards, when memory was measured in kilobytes, when engineers worked with tools and assumptions that no longer define modern systems. But they are still the ones reporting. We continue to rely on them, not out of choice, but because no alternative exists. The frontier they are mapping remains unvisited by anything newer, anything closer, anything designed with current understanding. And so the situation settles into something rare. A single pair of machines, aging, distant, irreplaceable, carrying the responsibility of observation for an entire region of space that remains otherwise unreachable. We are relying on two machines built when people use typewriters to tell us everything we will know about interstellar space. For the foreseeable future, that is all we have. Imagine reaching beyond every planet, beyond the last orbit, expecting silence, expecting absence, expecting nothing at all. But that expectation does not hold. What we call interstellar space is not a void. It is a medium, a thin and continuous mixture of gas, plasma, dust, magnetic fields, and high-energy particles that fills the space between stars. You are not leaving something behind. You are entering something else. The dominant state is plasma, a form of matter where atoms are stripped of electrons, leaving a sea of charged particles that respond to electromagnetic forces. This plasma in the very local interstellar medium carries temperatures between 30,000 and 50,000 degrees Celsius. That sounds extreme, but temperature here does not behave as you expect. With densities around 1/10 of an electron per cubic centimeter, there are so few particles that almost no energy transfers through contact. It is hot in measurement, but not in sensation. Heat needs density. Threaded through this plasma is a magnetic field, measured at roughly 4 to 5 microgauss, far weaker than anything you encounter in daily life, tens of thousands of times weaker than a simple refrigerator magnet. Yet across vast distances, it shapes motion. Particles follow it. Cosmic rays, some of the most energetic particles in the universe, move along these magnetic lines, guided across light years. Many of them were accelerated by supernova shock waves, the expanding fronts of stellar explosions that occurred millions of years ago. They are ancient travelers. As Voyager drifts, its instruments register these particles, counting their arrival, mapping their energy, revealing a constant flux that never fully stops. This is not background noise. It is activity. Interstellar dust moves with it. Tiny grains of silicon, carbon, and iron pass through the spacecraft's environment, detected as impacts or subtle signals. Each grain is a fragment of stellar history, material forged in the interiors of stars and expelled during violent endings. You are surrounded by remnants. The carbon that forms the framework of your cells, the iron carried in your blood, the calcium within your bones, all of it originated in processes like these. Stars lived, fused lighter elements into heavier ones, then scattered that material outward. And now it drifts. Voyager is moving through that same distribution, not as an observer from outside, but as an object embedded within it, measuring conditions from the inside of a medium that connects every star in this region of the galaxy. But the scale changes everything. The distances between particles are enormous compared to anything familiar, so interactions are rare, collisions infrequent, structures subtle and extended across vast regions. You cannot see it directly, but it is present in every measurement. It is not empty. It is structured, dynamic, and filled with motion that persists over millions of years, shaped by forces that operate across distances you can barely hold in mind. It is not empty out there. It is filled with the debris of everything that came before. Voyager is drifting through the ashes of dead stars. For a long time, the question existed without measurement. You could ask it, repeat it, build stories around it, but you could not anchor it to data. That has begun to change. Not by finding life, not by detecting signals, but by measuring the environment that life must survive within, the medium that surrounds every star and every planetary system in the galaxy. Voyager is inside that medium now. Its instruments are sampling the very local interstellar region directly, giving you numbers for density, magnetic field strength, particle flux, and temperature values that were once inferred only from distant observations filtered through layers of solar influence. This is a reference point. When you model another star, you now have a comparison. You can estimate how its stellar wind, the stream of charged particles it emits, interacts with the surrounding interstellar medium to form a protective boundary, a heliosphere in general terms, a magnetic bubble inflated by the star. Not all bubbles are equal. Their size and structure depend on two opposing pressures: the outward push of the star's wind and the inward pressure of the interstellar environment. If the surrounding medium is dense or strongly magnetized, the bubble compresses. If it is sparse, it expands. That balance determines shielding. Cosmic rays, high-energy particles accelerated by distant explosions, are partially deflected or slowed by this boundary. If the shield is reduced, more of those particles reach the inner system. They reach the planets. High levels of cosmic radiation can alter atmospheric chemistry, damage biological molecules, and increase mutation rates. Over long periods, this changes the conditions under which complex life can emerge and persist. But how much is too much? That threshold depends on factors we are only beginning to quantify. Voyager provides one of the few direct measurements of what a functioning heliosphere looks like from within under specific galactic conditions. Our conditions. The Sun currently resides within a region known as the local bubble, a low-density cavity formed by ancient supernovae where external pressure is relatively low and the heliosphere can maintain a larger extent. This may not be typical. It may be fortunate. If the Sun were moving through a denser interstellar cloud, the heliosphere could compress significantly, reducing its shielding effectiveness. Models suggest that under such conditions, cosmic ray flux at Earth could increase substantially, but the exact impact remains uncertain. Voyager's data helps constrain these models. It anchors them to reality, providing actual measurements instead of assumptions. When you extend those models to other systems, you begin to map not just where planets exist, but where environments might remain stable long enough for life to develop. But the answer is still incomplete. You are not detecting life itself. You are defining the conditions that allow it. You are narrowing the range of possibilities, turning an unbounded question into something that can be tested, refined, and compared. And that shift matters. Voyager did not set out to answer that question, but everything it has measured since 2012 reaches toward it. There was a moment when the payload was already fixed, trajectories calculated, instruments secured, and yet something intangible still felt unresolved. Not a measurement, a statement. The decision to include a record did not come from expectation of contact. The probability that another civilization would intercept a spacecraft crossing interstellar distances on such a narrow path is effectively zero within any meaningful timescale. That was understood. But sending nothing felt incomplete. It implied that when we first extended beyond our system, we chose silence, not because we lacked content, but because we declined to define ourselves. So the record was assembled. Anne Druyan later described it not as a message to others, but as a reflection of what we valued at that moment, a curated selection of sounds, images, and ideas that a small group of humans believed represented the species with some degree of honesty. Not perfection, selection. Carl Sagan resisted presenting an idealized version of humanity. When asked why the record included both achievements and imperfections, he explained that accuracy mattered more than impression. You were not presenting an image to impress. You were presenting a reality to acknowledge. But some choices were quieter. Druyan recorded her own brain activity, an electroencephalogram, a measurement of electrical patterns produced by the brain during a period when her thoughts moved through history, biology, and something more personal. She had recently fallen in love. That detail was not announced. It was encoded into the signal itself, carried outward as a pattern of electrical variation translated into sound, now moving through interstellar space as part of the same record. You cannot hear it directly, but it is there, embedded among greetings in 55 languages, alongside recordings of wind, rain, surf, and animal calls, including whale song and the first words spoken by a mother to her newborn child. There is also music. Bach appears, as does Beethoven, but also a Navajo chant, an Azerbaijani folk piece, a Peruvian wedding song, and a recording of Johnny B. Good. These are not random selections. They are judgments. They reflect what a group of individuals, constrained by time and medium, believed could stand in for the diversity of human experience, compressed into 90 minutes of sound and a set of encoded images. But the context extends further. In about 40,000 years, the spacecraft carrying this record will pass within 1.6 light-years of the star Gliese 445, a close approach on astronomical scales, but still distant in absolute terms. By then, the civilization that created it will have changed beyond recognition, or ended. The record will continue regardless, preserved in vacuum, designed to endure for up to 1 billion years, far longer than any structure currently standing on Earth. It was not built for utility. It does not transmit data back, does not assist navigation, does not contribute to the spacecraft's operation. Its purpose is entirely representational, a decision to carry something of ourselves outward, even without expectation of reception. But that decision holds weight. They knew it would almost certainly never be found. They built it to last 1 billion years anyway. That choice says something about us. At this moment, without announcement or pause, a signal is already on its way toward you. It left a distant transmitter more than 22 hours ago, moving at the speed of light, crossing billions of kilometers of sparse plasma, threading through magnetic fields and drifting particles, carrying with it a narrow stream of encoded information. By the time it arrives, it is old, but it is intact. Right now, the spacecraft sending that signal is about 173 astronomical units from the Sun, roughly 25.8 billion kilometers from the world where you are listening. Distance at that scale resists intuition. You can calculate it, you can repeat it, but it does not settle easily into the mind. But the signal settles. It reaches large radio dishes on Earth every day, detected as a whisper far below background noise, about 20 billion times weaker than the energy needed to power a small digital watch. Engineers isolate it, amplify it, translate it, and recover meaning from something that barely exists. And yet, it persists. That persistence is not accidental. It is the result of decisions made decades ago, when a group of engineers and scientists, many in their 20s and 30s, designed a machine with margins, redundancies, and tolerances that exceeded the expectations of their time. They built it to last 5 years. It has been operating for more than 47. It has traveled beyond every planet, crossed a boundary no instrument had touched, and entered a region that had only existed in theory. It has continued to function not because conditions are forgiving, but because the design was careful. But it carries more than instruments. Fixed to its structure is a record, gold-plated, encoded with images and sounds that represent a narrow slice of human experience, chosen not for completeness, but for meaning. Rain is there. Ocean surf is there. The first words spoken by a mother to her child are there. These are small things, but they were chosen. But what does that choice say? We built a machine to measure fields, particles, and plasma, yet we also gave it something unnecessary, something that does not assist navigation or communication, something that exists only as a gesture. We chose to include music. We chose to include voices. We chose to include evidence that we are not only observers, but participants in a story that extends beyond measurement. The record will likely never be found, never be decoded, never be heard by anything that did not already create it. But it is still there, and the signal continues. Each day, across 22 hours of travel, it arrives again, carrying updated measurements from a place no human will visit, from a machine no human will touch again. It confirms that the spacecraft is still operating, still oriented, still sending, still connected. Not by proximity, but by intention. It has shown that the space beyond our system is structured, active, and filled with processes that reshape what we thought we understood. But alongside that, it reflects something quieter, something less measurable, that we reach outward, that we continue to listen, that even at these distances, we maintain a connection to something we created, not because it is easy, but because it is possible. The signal is still coming back, and so are we.